We give in this video a brief presentation of the support vector machines, what they are, what they do, and how to train one based on a dataset. I only discuss them here in a nutshell. I have several other videos where the mathematics of support vector machines is discussed in details, and I refer you to those for the details. So the problem in support vector machines is one where you have to classify a dataset. We have two classes, so the labels are coming in the form of being -1 for one of the classes and +1 for the other class. And the objective is to find the hyperplane separating the two classes. And this is suggestive in this picture here. You have one class here and the other one here, and you have this sort of line. In two dimensions, hyperplane is a line, and in fact you would like to have a sort of a wider margin, not just a simple line, to separate these two classes. And so the objective is really this, that you would like to maximize this margin. You would like to have as clear separation between the two classes as you can possibly have. So you have a data set, let's denote this by x, and this consists of a number of data points, xt, and their labels. And these labels are, as I said, either -1 or 1 for all data points, and that defines the class where the data point belongs to. And the problem in support vector machine is this one. You would like to find, so problem it's find vectors w and w0 which have as many dimensions as your data points have, in such a way that you have on one hand the dot product, or w transpose times xt plus w0, to be at least 1 for all those data points for whom the label is equal to 1, and w transposed times xt, or dot product between w and xt, plus w0 is smaller than or equal to -1 for all those data points for whom the label rt is -1. And so I just want to comment already here that there is this idea that obviously you would like your data points to be on either side of the hyperplane. You want these ones to be on the positive side of the hyperplane, and these ones coming from the -1 class to be on the negative side of the hyperplane. But even more than that, we are asking that there is a margin, that in fact your data points on the positive side are in fact even beyond this margin equal to 1, and these ones are beyond the margin of -1. So this captures this idea that you would have a wider margin separating the two classes. And this can be rewritten obviously just by taking advantage that we have these labels 1 and -1, so we can multiply with the label. And what this does, when you multiply with the label 1, obviously this doesn't change, but this one is going to change the sign of the inequality, and that's going to give you 1. So I'm going to have just one single condition capturing both of these conditions. So the way this goes is, so this is equivalent with the product between the label and w transpose times xt plus w0 being larger than or equal to 1, and this is now valid for all the data points regardless of what the label is. So the whole idea is that we would like to find this margin, and we would like to enlarge this margin as much as possible. So if we take a look on this small example, we have a number of data points. Those coming from say the negative class are just shown in red in this figure, and the ones coming from the positive class, they are coming with blue and indicated by crosses in this dataset. And so the point is that we would like to find this hyperplane indicated by this continuous line in here in such a way that there is a margin around this, a margin at distance +1 on one side and at -1, in such a way that this margin is as wide as possible. So you can see already in this figure what the problem is. You can enlarge this margin as much as you want, but you can only do that until the margin starts touching on the first data points in your data set. So in our case, starting from some line that we suspect might be a good solution, we start enlarging the margin. And the moment you touch on one side, you are going to stop, and you can continue enlarging on the other side until you touch the first points from the other class. And then, of course, you recalibrate this line to be in the center of your margin. And these data points that are touching the margin, they are going to be the ones, in fact, that will define the whole model, and they are going to be called the support vectors of your model. And I'm going to come back to this point, but maybe I just point out already now that the interesting part of this support vector machine, and in some ways the crucial part, is really that most of the data points in your data set don't really play a role in giving the solution to the problem. There are only a few of the data points that help define the solution to the problem, and they are these that we call support vectors, and hence also the name of the model being a support vector machine, in the sense of a machine, a model, as defined by a few of these data points. So the equation of the hyperplane we are looking for is, as we commented already, it's W transposed times data point xt plus W0 is equal to 0. So that's the equation of the hyperplane. And for a data point, the distance to this hyperplane is, so distance from the data point xt to the hyperplane. So this we know from geometry, that the distance is going to be the norm of W transpose times xt plus W0 divided by the norm of W. And I mean this distance is really going to be positive or negative depending on which side of the hyperplane the point is. And because we have the label RT being -1 or +1, we can multiply with the label to get a quantity which is always positive. And so we introduce this product between the label RT of this data point and W transposed xt plus W0 divided by the norm of W. And we would like this to be, maximal. We would like this to be at least some value rho that we are going to reason about in just a moment. So the objective for us is going to be that for all data points, we have this distance where we multiply with the label, so that we always have a positive quantity in our hands. So this one should be as large as possible. So I'm going to write it like this: larger than or greater than or equal to rho. And this rho, our objective is going to be to maximize. And so that's the formulation of having as wide a margin as you possibly can, separating the two classes of your data set. Now, one observation is that we can in fact get an infinite number of solutions to this problem, an infinite number of vectors W in a trivial way, simply just by keeping its direction and just choosing different values for its norm. And we in fact would like to fix some of these issues, and in fact we would like to get a problem that has a unique solution. And to do that, I mean, we have to fix the norm of W to some sort of a suitable value. And for us, a very convenient way to do that is going to be, we are going to choose the solution. I mean, if we are to report just one solution, we are going to report the solution W such that rho times the norm of W is equal to 1. So out of the many different options we have for W, we are going to choose the one that has norm 1 over rho, just to simplify the equation and to get a unique solution to the problem. And so what you can see here, I mean, once we fix this idea, all of a sudden we have this consequence that the problem of maximizing rho is going to be the same as the problem of minimizing the norm of W. And so the problem now can be formulated in terms of a minimization problem where the focus is on minimizing W, and this can be written in the following way. We will say the problem is minimize the norm of W, but just to simplify the mathematics, in fact, I'm going to say minimize the square of the norm of W. And again, for reasons that have to do with calculating partial derivatives, I'm going to put 1 over 2 in front. But this is the same thing as minimizing the norm of W. And this is going to be subject to the following constraint. We want to have RT times W transposed XT plus W0 to be greater than or equal to, and obviously, I mean, what we have from this one is going to be rho times W, but with our convention that we are looking for the solution with rho times W equal to 1, what I'm going to write in here is just 1, but it's just a reformulation of this condition in here. So this is greater than or equal to 1. So this is a problem in two unknowns, in W and W0. Obviously, these are vectorial variables that have as many components as your data set has. And to solve this problem, we can use the idea of a Lagrangian. And that idea is that you can integrate these constraints into your optimization objective. And in the case of our problem, this is how it goes. We are writing the Lagrangian. I'm going to denote this by L, and I'm going to put P in here in a sense that is the Lagrangian of the primary problem, but I'm going to come back to this in just a moment. So the Lagrangian is, as usual, you have your original objective function, which is 1 over 2 the norm of W squared. And then the other idea is that for all of your constraints, you are going to introduce some so-called Lagrange multipliers, and you are going to have the constraints integrated into your objective function into the Lagrangian in the following way. You have a sum, so this is going to be for all the constraints you have, and there were as many constraints as you had data points, so it's going to be a sum for all the data points. And here is the Lagrangian multiplier for the current data point, and this is going to be multiplied with RT times W transposed times XT plus W0 minus 1, which is essentially coming from the constraint we had. The constraint was that this product should be greater than or equal to 1. And when you write the Lagrangian, you just move this to minus 1, and then you move this 1 on the left-hand side, and you multiply it with this Lagrangian multiplier. So this is going to be our new objective function to optimize, and we can just open the parentheses in here, and we will get that this is 1 over 2 the norm of W squared minus, and I have the sum from 1 to n. I do nothing else but just to open the parentheses here for this minus 1. And so on one hand, I have this product is going to be alpha t times RT times W transpose times XT plus W0. And then it's plus, and that's the term corresponding to this one, plus sum from 1 to n by alpha t. And the objective here is that we would like to minimize with respect to W and to W0. And I comment in just a moment why is it a maximization by all these alpha t, or by the whole vector alpha of the Lagrangian function. Now, the comment of these Lagrangian multipliers is that they are in fact penalizing for any breaking of the constraint. So for any point that satisfies the constraint, this alpha is going to be optimized to 0. Maximizing by alpha is really to minimize the part after the minus, and that gets minimized for alpha equals 0. for any point that breaks the constraint, the alpha can be arbitrarily large, and that's going to lead to a large value of the Lagrangian, which will thus be avoided in the minimization problem. So all in all, there is this idea that the goal, if you think about the alpha, is going to be to maximize this alpha, and obviously the objective for W and W0 is going to be just like before, solve the minimization problem with respect to them. And here is how we start thinking about solving this problem. I'm going to just repeat this Lagrangian so that we have it in front of us. So the Lagrangian I had on the previous slide was LP is equal to 1 over 2 the norm of W squared minus the sum from 1 to n by alpha t RT times W transposed xt plus W0 plus a sum from 1 to n by alpha t. And the objective is to minimize, so minimize by W and by W0, and maximize by alpha. Alpha is the vector, collecting all these coefficients alpha t, maximize the Lagrangian LP. And this was subject to all these alpha t being greater than or equal to 0 for all t. And at this point, we can in fact apply the so-called Slater's condition. And this is a condition, I skipped the details in here, but it's essentially saying that for well-behaved problems, in a sense that I don't define in here, these two optimization objectives can be commuted. And so when we are applying the Slater condition, the problem is going to be, the equivalent objective is going to be maximize by alpha and minimize by W and W0 this Lagrangian, and obviously the constraint remains the same. So alpha t is greater than or equal to 0 for all t. And so at this point, the problem becomes quite much easier, because minimizing by W and W0 leads us to consider the partial derivatives of this Lagrangian with respect to W and W0 and making them equal to 0, and out of there getting some new conditions that is going to help us to simplify this Lagrangian. And here is how this goes. The partial derivative of the Lagrangian with respect to W, we are going to set this to 0, and that's going to imply, when we calculate the partial derivative, is going to imply that W is going to be equal to this whole sum alpha t RT xt. So that's already a great advance, because it means that when we focus on the other problem of maximizing by alpha, we are going to find these solutions in terms of alpha, and that's going to give us also right away the solution in terms of W. So this is a great project in that sense right away. The other condition was we take the partial derivative of the Lagrangian with respect to W0, and we set this to 0, and that's going to imply, when we calculate the partial derivative, that is going to be the sum from 1 to n by alpha t RT, that's going to be equal to 0. And now we take these two conditions and we plug them into the formulation of the Lagrangian, and when I do that, I'm going to get the so-called dual Lagrangian, which is nothing else but the form of the primary Lagrangian, where I'm using these conditions that I got from setting the partial derivatives to 0. So I'm just plugging these into our objective function, and this is going to be now denoted by LD. So this is the so-called dual formulation of the Lagrangian. So this is going to be 1 over 2, and it's the norm of W squared, and I'm just writing this in a different form, but it's essentially the same thing, norm of W squared, but I'm writing it here just as W transposed times W, so that I'm continuing with this so-called dot product, where you see the product between two vectors rather than norms. And then in the Lagrangian we had the following term, and I just take W transpose in front, and it's going to be W transpose times sum by T of alpha T RT XT minus W0, a sum by T with alpha T RT, and there was also this last one, sum by T of alpha T. And so this is now equal to, and you see, because we got this condition that the sum of alpha T RT is equal to 0, then all of a sudden this term here collapses, and also what we have is that this sum right here is W, so I'm going to get a W transpose times W, which is exactly what I had here with 1 over 2 in front. So these two get combined so that we get minus 1 over 2 W transposed times W, and then there is only the last term remaining, which is sum by T from alpha T. And now I'm continuing to introduce this form of W into this objective function in here. So what I'm getting is that this is equal to minus 1 over 2, and then it's going to be a sum by T and sum by S. So maybe I'm writing here, so it's sum by from 1 to n, 1 from S from 1 to n, and it's going to be alpha T alpha S S R T R S times XT transposed times XS, and then I have the remaining term, which is the same as before, sum by T alpha T. So this is going to be now the objective is going to be in this dual formulation of the problem. The only remaining objective is going to be to maximize this dual Lagrangian with respect to all of these coefficients alpha T, subject to on one hand we have that alpha T is greater than or equal to 0, which we had before, and on the other hand we have this remaining constraint in here that we still have to carry with us, and so it's subject to that was one condition, and the other condition was sum by T alpha T RT is equal to 0. And this, in fact, now we can see right away that we can solve this problem using quadratic programming, and the problem has in fact a unique solution. And the other thing that I want to really observe in here is that now all of a sudden we have n variables in this problem. We have as many variables as there are data points in your problem, and not the number of features as we had before. And even more than that, when you start looking into this problem, you realize that many of the solutions, in fact really most of them for a non-trivial data set, will get their alpha equal to 0, and this is something I commented before. It corresponds to this idea that these data points that end up quite far away from the margin, they will get their alphas equal to 0. So when we have these Lagrangian where we have all of these sums, in fact most of these alphas are going to be equal to 0. There are only a few of them non-zero. So in fact this becomes a very simple model in general for non-trivial data sets. And the points where we have alpha T, so I'm just writing on the figure. So my point was that if this was point, say, xi, the alpha I for this data point is going to end up equal to 0. And if this was point, say, xj, the alpha for this one also ends up equal to 0. This one is also outside the margin, even though it's quite close to it, but it ends up being outside the margin. And so if this was point xk, also the alpha for this one will end up equal to 0. And the same, is going to be also for this data point. This one will also have its alpha equal to 0. So the only ones where we have alpha t non-zero, so alpha greater than 0, are going to be these data points that we have in our figure with a circle around them. These are the ones that contribute to defining the solution. If you think about the solution in terms of the original problem, what's our hyperplane, this W is going to be defined only by these vectors where alpha is non-zero. So only by these vectors that are really, on the margin. So for any one of these data points sitting exactly on the margin, what we have is that the RT times W transposed times XT plus W0, this was the distance from the data point to the hyperplane. This is exactly equal to 1. So this is true for all of these data points sitting exactly on the margin, whether it's the +1 margin or is the -1 margin. That gets solved, as we discussed before, by multiplying with this label. So the point here is that W gets calculated from this condition, and for any one of these data points sitting on the margin, we can just use any one of them to calculate this W0. In practice, in fact, we are taking all of these data points sitting exactly on the margin, and we will get the value of W0 from each of them. And just because we do a lot of numerical calculations in here, just to allow for these numerical inaccuracies, very often in practice you get an average of all the values you get for W0 for these points sitting in a margin, just for numerical stability. So all of these considerations, they were assuming implicitly that we have a data set which is separable. So we were assuming that in fact the problem that we are looking for, finding a hyperplane, separating the two classes, so this problem, we were assuming implicitly that it has a solution. So the only thing that we were concerned with was to optimize it, find W and W0 in such a way that this margin should be as wide as possible. In practice, however, you might have a data set, and you will have a data set most often, which is in fact non-separable. There is no way to find a hyperplane that really separates neatly your data points into the two different sides of the hyperplane. So you will have errors in the final model that you end up with, meaning that you will have data points that sit on the wrong side of the hyperplane, or in fact sit within the margin, so not outside this margin that you are going to optimize. So for this case, we need a slightly different formulation of the problem, where we are allowing for the idea that there will be errors even in the final optimized solution to the problem. So I'm discussing next the case of non-separable data, and you will see that we plug in some sense this idea that you have errors, but other than that, it goes very similarly. Again, we are going to have a Lagrangian, and again we will have this idea that we optimize that Lagrangian, we get some conditions, and we get the dual Lagrangian, and the problem goes pretty much in the same way like in here. But the starting point, the formulation of the problem is just slightly different to allow for the concept of having errors in your data. So here is how this goes. So in this case, we have these data points, and we can see that, we will have a solution for these data points in such a way that some of them are correctly classified. They are on the correct side of the plane. These ones right here, this one is also on the other side, on the negative side of the hyperplane, and that's completely fine. That's what we would like. All the blue crosses to be on the positive side, and all the red dots to be on the negative side. And we will have our support vectors, and they will define the optimal solution to the problem just like before. This is this one, and these red dots on the other side of the margin. But what's changed here with respect to our discussion from before is that you allow for the concept that there will be no way to avoid errors, and the errors might be of different types. One error might be that, for example, this point is on the correct side of the hyperplane. In that sense, it's correctly classified as being on the positive side of the plane, but it's not really as cleanly as we would like it to be. It's not outside the margin, but in fact inside this margin, and that's an error in the sense of our model at aiming to have all the data points pushed outside of the margin. The other type of error, which is shown through this data point in here, is that some of your data points are going to be in fact incorrectly classified. They are going to be in fact sitting on the wrong side of the hyperplane. And so there is this idea that when you look for the ideal, for the optimal hyperplane, there will be this kind of errors. For many of the data points, hopefully most of them, you will have a correct classification. Some of them are going to be of help to you in terms of being support vectors and defining the solution. But for some of them, there will be errors, and there is nothing you can do about that. And the objective now is going to be, in some sense, to quantify these errors and to minimize for them in the optimal model. We will have, just like before, the same idea that we will have the distance between the data point and the hyperplane. And just so that we are working with positive numbers, we multiply with the label, which is +1 - 1. So just like before, this is W transpose times xt plus W0. And remember that the idea was that we would like this to be greater than or equal to 1. But because we realize that, there might be errors, and those errors we are going to include in this formulation of the problem through these extra variables. There is going to be one variable for each one of the data point. This xt, they are the so-called slack variables, and they will be standing in here for the idea that there is an error, and we are going to try to minimize for these slack variables. And the point is that if somehow in the optimal solution you get for a data point this variable ct to be equal to 0, then there is going to be no problem for the data point. It's correctly classified, it satisfies the constraint in the way that we liked to have it. It's on the correct side of the hyperplane and outside the margin. If this slack variable is in fact between 0 and 1, what this means is that still you are on the correct side of the hyperplane, like this point in here is just that you are not outside of the margin, but rather within the margin. But you are correctly classified. And on the other hand, if you have the slack variable ct greater than or equal to 1, then xt is going to be misclassified. So it's the case of this one here. The point should be really outside in here, but this slack variable being greater than or equal to 1 shows that in fact the data point is being pushed by the hyperplane that you chose, is being pushed or is being is being left on the wrong side of the hyperplane. So for such points, they will be misclassified. So what we end up with is, if we think about how many misclassifications we have, the number of misclassifications is going to be exactly the number of how many of these ct are larger than 1, and the number of non-separable points, so including those in the margin, is going to be the number of how many of these variables ct is larger than 0. So we would like to minimize for the number of these variables that are greater than 0, and rather than thinking about how many variables you have, we can introduce a so-called soft error, which does a good job of capturing this concept, but it does it in a way that allows us to work with calculus. So in fact, we don't do the number of variables that are greater than 0, but in fact we are going to say, you know what, let me just take the sum. and I'm going to have this sum for all the data points. Remember that these xi, we are having them greater than or equal to 0. So when I'm doing this sum, as we have in here, in this sum, we will have contributions only from those variables that are greater than 0. So in that sense, we don't get the number of variables greater than 0, but we get their sum. And so in that sense, it's a so-called soft error. It's not exactly the error that we conceptualized about, but it's something that does a good job, and at the same time, it's in a form that allows us to work with calculus towards finding a solution for the problem. So here is how we are continuing with this. We are going to introduce this soft error as a penalty term in our Lagrangian. So the way we are writing our Lagrangian is, is going to be the same as before, with the same reasoning. We want to minimize the norm of W, and for that I'm writing, just because it's easier with calculus, the norm squared, and I put a 1/2 in front of it. But this time I'm going to say, yeah, but it's also about minimizing the error. So how about if I introduce this soft error as an extra term in the Lagrangian, and I'm even going to have a sort of an extra quantifier in here just to have added flexibility. So this is just the sum by xi t for all the data points. And this is going to be subject to the constraints, so xi t greater than or equal to 0. And C is this so-called penalty factor, and this was the same in any other regularization scheme that we've discussed about in other types of machine learning models. So the discussion now continues exactly the same as in the separable case. We realize that we have this Lagrangian that we have to minimize, and our constraints are going to be that xi t is greater than or equal to 0, and the other constraint, just like before, is that rt times w transposed xt plus w0 is greater than or equal to 1 minus xi t. And so we have the same idea as before. We are going to add these terms, these constraints, to the optimization objective, and we do that through these so-called Lagrange multipliers. And so what we end up with in the end, I'm going to use the same notation LP. I hope that this is not confusing, but it's going to be a different function, but just the idea that it's a new objective function, but it's the same concept of this being a Lagrangian. So what we have is the same as we had before, 1/2 norm of w squared plus c times the sum of these xi t, t from 1 to n. And then we have this idea that we introduce these constraints into our objective function. On one hand, I'm going to take care of first of this second constraint, this one here. And for this one, I have the constraints alpha, very similar as before, sum by t, alpha t times, and we have rt w transposed xt plus w0. And remember, the idea was that we move everything to the left hand side, so this is -1 plus xi t. And then the other term I'm writing takes care of these constraints, and for them I'm introducing new Lagrange multipliers in the form of these coefficients mu t, and they will be multiplied with xi t. And so it's the same as before, except that now we have two constraints, and so we have two sets of Lagrange multipliers. But the concept remains the same, that we are adding them to the optimization function. And these are Lagrange multipliers, so all of these alpha t have to be greater than or equal to 0, and also mu t have to be greater than or equal to 0. And the objective is, minimize by w and w0, and at the same time is going to be a maximization. And you can see that it's a maximization with the same argument that we had in a separable case. It's a maximization by alpha and mu for this Lagrangian multiplier. And again, in here, because these are so well-behaved functions, we can apply the Slater's condition, and that's going to allow us to, again, conclude that, in fact, these two optimization objectives can be commuted. And so we are going to end up with the problem where we first minimize by W and W0, and only then we maximize by alpha and mu. And that's going to open the door to us to introduce the partial derivatives of LP with respect to W and W0 and get some extra conditions from there, and then plug them into this Lagrangian and think about the maximization by alpha and mu. The partial derivative of the Lagrangian with respect to W is W minus sum by t alpha t rt xt, and we set this to be equal to 0. And from this, I mean, we get right away that W is equal to sum by t alpha t rt xt, and that's very similar to what we had in the separable case. Then on the other hand, we have the partial derivative of the Lagrangian with respect to W0. This is sum by t alpha t rt is equal to 0. And then we have the partial derivative of LP with respect to xi t, and that was c minus alpha t minus mu t, and we set this one to be equal to 0 for all data points t. And so because so what this implies is, simply because mu t is greater than or equal to 0, what this implies is that we have these coefficients alpha t between 0 and c for all data points t. And the discussion now is very similar to what we had before. All of these data points that are correctly classified, they will get their alpha t to be equal to 0. So for many of them, most of them, hopefully, this alpha t is going to be equal to 0. And so what this means is that when we take a look at how this solution, the optimal hyperplane, is defined, we realize that in fact in this sum, even though it looks like there will be a contribution from all the data points, in fact you will only have contributions from those data points that are sitting within a margin or inside these margins. For those that have alpha t larger than 0, we have this idea that they are the support vector. So they are the ones defining our W, and they are indicated in this figure with these circles around the data points. Now, out of these support vectors that define our solution, we can look at the alpha t to decide that they are, you know, in a margin or within a margin band or even misclassified. So we distinguish between them because these ones that are exactly on the margin, they will have their alpha t smaller than c, and obviously also 0 smaller than this one. The same is going to be here. Alpha t is going to be smaller than c, and obviously also larger than 0, and the same is going to be here, alpha t between 0 and c. And in fact, for these data points inside the margin, we will have alpha t equal to c. So this one here will have this one, and alpha t equals c also for this one inside the margin, or even, you know, being misclassified. So the error of the model is going to be measured in the following way. This is I'm just writing this. It's a so-called hinge error or hinge loss of the model. If you have the predicted class of the model and you have the real label of the model, this is going to be 0, so there is no error if yt rt is greater than or equal to 1, and it's going to be 1 minus yt rt otherwise. And the intuition of this hinge loss is that it just quantifies this error in terms of whether you are on the wrong side of the margin and how far away you are from this margin. One comment I still want to make is about this regularization parameter C, which has an influence on these values on the domain that your alpha coefficients can take. And this is really a regularization parameter in the same way that we've had it in other machine learning models, for example in regression, and it defines a trade-off between maximizing the margin and minimizing the error. And so the way this goes, and the way you should think about it intuitively, is that if you take too large of a value for this regularization parameter, you are going to impose quite a high penalty for the non-separable points. And so we will get more support vectors and a sort of a narrower margin. And so the result of that intuitively is that your model is going to follow, maybe in some sense too faithfully, your data points. It's going to give too little slack for errors. And so at the end of the day, this is going to be obviously a case of overfitting. On the other hand, if you take a value of C that is too small, you are going to penalize too little for these non-separable points. And so in that sense, you are going to end up with a underfitting problem where you are not really following enough the trends of your data point to find the optimal margin. So this is a matter of experimenting with and maybe testing models with different values of C. There is a way to do that through cross-validation, and we will have a video discussing cross-validation in a general sense at some point later on.